let's look at a trivial data set here. So I have two classes, a training set here made of crosses and circles. And in this particular case, I've used this RBF kernel, the Gauss kernel. And well, you see that these are very few observations. So we do get, using the kernel trick, we get a nonlinear solution, which is fine. However, I would also argue that this will be an overfitting to our data because we have very few observations, and just based on a single observation here, we decide to make this complex bend up here. In fact, I generated the data, so I know what would be the base classifier, what would be the best possible classifier. And in this particular case, the way I generated the data, the best classifier averaging over many training sets would just be a vertical split. Okay? So in other words, so far we have regularized in the sense of among all possible solutions in this high-dimensional space to which we implicitly map using the RBF kernel, we have found a solution that lies furthest from members of both classes. And the closest members are here circled in red. These are the support vectors. But this looks like an overfitting to our data. Or I will give you a low-dimensional example. So So based on this data set, you would guess, okay, your classifier should be something like that. But now we have a single observation of this class out here. And if we just follow a standard procedure, we would now get our classifier shifted to this corner. Now, perhaps given 5 examples, this might not look like an outlier, but if I have 1,000 points here and a single one out there, you wouldn't really want to believe this single point. So the question is if we cannot somehow make this more robust with respect to outliers. Or in the example that I've just shown, if we cannot find a solution with a wider margin than the one you've just seen. And yes, you can. And this is called the soft margin support vector machine. So previously, we requested really that no point lie on the wrong side of the margin, hence hard margin. And we can instead introduce slack variables. So Schlupf in German. And thus relax the problem a little bit or regularize it. So I'm going to minimize as before over 1/2 times W transpose W. And before, the condition was that Yi xi transpose W should definitely leave a margin of at least 1. So it should really certainly respect this margin. And we can now introduce some slack. It says, okay, in some examples, we're going to accept a deviation from our principle of xi. So for instance, in this example here, I could say that this is the classifier I'm going to construct. And this is the slack by which it lies on the wrong side of the margin. So the margin goes up to this point, so I need to measure the slack from the beginning of my margin, and this slack would be this variable xi associated with this particular observation here. Now, okay, all these slack variables should be larger than or equal to 0. But if I now optimize with respect to both my weight vector and the size, there's nothing that prevents explaining everything with slack variables. So I need to somehow penalize this. And I do so by adding the sum of all the slack variables and weighting this contribution with this factor C. So this is a user design parameter. I've picked C for cost here. And it's important to note that this is a design parameter, because if you use support vector machines in the real world, this is something that you need to choose in a sensible fashion. The other important parameter being the parameters of your kernel. So the sigma here, or power r here, or kappa theta there. Okay, and I will do this explicitly, but the formula will be very similar to what you've seen before. So we again set up a Lagrangian. So besides W, we now have our new variables, the slack variables, and we also need an additional Lagrange multiplier to enforce this set of constraints here. Okay, this is what we've seen before, and except that we now have relaxed this constraint, and now we need this additional Lagrange multiplier for this additional constraint. Inequality constraint. Okay, and here both alpha and mu should be larger than or equal to 0. And we can now differentiate as before with respect to the weights, which will give us W minus so, and we request, as before, we want to minimize with respect to W. So we get the same equation that we saw before. The W0 is given by sum over alpha I yi xi. And secondly, we differentiate with respect to this new variable. So here, the contribution is C. Minus alpha I minus mu I. We want to also minimize with respect to these variables, and we find that at the saddle point we have that C equals alpha I plus mu I. Okay, then we can build the Wolfe dual. So we insert the optimum weight vector and the optimum slack variables and want to maximize the remainder with respect to the Lagrange multipliers. So C I can replace by alpha I plus mu I. This expression here is given by W0. So I have minus W0 transpose W0. And now I need to collect the remaining terms. Okay, now luckily this simplifies. We have here the sum over psi I times mu I, which cancels with that. And we have the sum over psi I alpha I, which cancels with this one here. Giving us minus 1/2 I write it out immediately. So inserting now again what we had found for W0. And we had a remaining term here, which was plus the sum over all alpha I. Okay, now we have these conditions, so we want to now maximize this. And we still have the condition that the alpha I should be larger than or equal to 0. And we had the condition that the mu I should be larger or equal to 0. And we had found that C equals alpha I plus mu I. And so I can say that alpha I equals C minus mu I. And we know that mu I was supposed to be larger than or equal to 0. So if mu I is larger than or equal to 0, it follows that alpha I must be less than or equal to C. So, or I can write this in a single line by saying okay, now if you compare what's written here so the optimization problem for the soft margin SVM to what we had derived before for the hard margin SVM, then it looks like a tiny difference. So this part is the only difference, that we now have an upper bound given by this user design parameter C. We now have a hard upper bound on our Lagrange multipliers. And this tiny difference in the expression, well, that makes for big implications if you now compute this for real problems. So since we also still have pairs of observations here, you can kernelize this just as before. So again, I want to show you a few examples. I didn't so I've copied down term by term what was written up here, and I've used this condition, which only holds when I differentiate. So when I set this to 0. So by writing my constraints in such a fashion, I have acknowledged that C equals alpha I plus mu I, which is only true for psi 0. More questions? I didn't understand the question. So to perform classification, I solve this optimization problem, and then the weight vectors are given by this expression here. And if I now want to classify an observation, I simply compute the or to write it in a general nonlinear fashion. So this would be classification. This would be for the linear case, or if we use the kernel. And now we only want to know if this expression is greater or smaller to 0. And that gives us the classification of this previously unseen sample X. And this is, by the way, also the sense in which SVM is so similar to radial basis functions, because you see these are, in particular if you use the Gaussian kernel, these are just kernels located at some of the observations, only at some of them, so only on the support vectors. And I simply take a weighted sum of my kernels to produce an estimated label. So this was my toy data set, and for the hard margin SVM and some Gaussian kernel for a given choice parameter, this was the solution that we obtained. And now I use the same standard deviation, but now I admit some slack. So by setting this, well, here I wrote P on the blackboard, it was C. By setting this cost parameter to infinity, I get the hard margin case. By setting it to only 110 or 1, I obtain increasingly wide margins. So the consequences are twofold. On the one hand, I now have more support vectors, so the yellow lines always indicate the width of the margin. So my margin has become wider. I have more support vectors, making my overall predictions, or making the method less sparse. But I have regularized more. So this is a much simpler classifier than that one, and it's much closer to the ground truth that I told you, namely the optimum classifier that would be just a vertical line. Okay, so for this given very small number of points in a 2D space, you would probably, without knowing the solution beforehand, you would be best advised in regularizing strongly, so to take this solution here. I have a few more examples. This is our famous data set that we always used when looking at you know, the Bayes theorem and so on. So if you remember, the Bayes classifier looks roughly like the black line here, but it has this small appendix also. And here again, for a given choice of the width of the RBF kernel, there are different solutions here, and well, if we regularize strongly, we get something very similar to QDA in this case. This is again this toy data set. Now keeping the cost, so up here keeping the cost of the slack variables fixed, but changing this time the parameter in the Gaussian kernel. So this was, I think, the solution that we had previously seen. And now if I make the Gaussian kernel very narrow, I obtain a highly flexible classifier. Actually, this is something like the one nearest neighbor classifier. So in this example, practically every point becomes a support vector, and you know, clearly a total overfit to the data. I get this very complex margin. And then as we take broader and broader kernels, we also help to regularize the problem. And for broad kernels here and admitting slack, I get a solution that's not so bad. And so, by the way, in this high-dimensional space, this black line is just a straight surface. And those yellow lines, the margins, are parallel surfaces. But mapping them back in this nonlinear fashion to this low-dimensional space, this is what it looks like. So it takes a while to get used to it. I'm not sure if it's intuition, if it can be called intuition, or just getting used to it. But either way, looking at it several times helps. Again, the complex distribution, keeping the penalty on the slack variables fixed and looking at different parameters for the RBF kernel. For very narrow kernels, total overfit. For broad kernels, reasonable solutions. And here's an illustration for a change of the polynomial kernel. If you take polynomial kernel of order 1, you just get a normal linear SVM. However, I had admitted some slack, so this is why some observations here lie inside the margin. And then on the other hand, here's a, if I take it to the second power, you know, some quadratic decision surface, third power, fourth power, and so on. So, a few remarks on the SVM. So, we had now looked at the soft margin SVM, and essentially this allows for further regularization at the cost of introducing this additional parameter. So to wrap up discussion of normal support vector machines, let's look at a few properties. So what are the characteristics? The characteristics are this concept of using a wide margin, which was originally motivated by statistical learning theory. I've mentioned to you once that statistical learning theory has two meanings. On the one hand, this whole discussion about Bayes' theorem and posterior probabilities of one class and the other expressed in terms of class densities and so on. And on the other hand, it has a distinctly technical meaning that is described, for instance, in the book by Wapnick and Trevonenkis. So the inventors of the support vector machine. And they derive distribution-free bounds on the optimism that a classifier has. So if you remember our discussion about the training error going down as you increase the capacity or the flexibility of your classifier, and the test error going up beyond some point, and the difference between these two curves was the optimism, and they have derived a probabilistic and distribution-independent bound. And this bound has as an ingredient the VC, or Wapnick-Trevonenkis dimension, and you can show that so the higher the VC dimension, the greater this discrepancy between training and test error. And for some classifiers, this, or let's say generally speaking, this VC dimension is a function of the margin. So the wider the margin, the smaller the VC dimension, and this is why this is a good regularization strategy. So wide margin helps us regularize the problem. Then we have the dual formulation as a quadratic programming problem. And this affords, so this formulation happens of a convex problem. First of all, so this is not a property of the dual formulation. This also holds for the primal, that we have a unique solution. But this dual formulation in particular also shows why we get sparse classifiers out. So classifiers in which only a fraction of the training set will be support vectors. And then there is the kernel trick, which makes a method that is originally linear only applicable to nonlinear problems. So empirically, we can say that overall, support vector machines enjoy pretty good predictive power. So it's a good method to use, and again, it's very nice that we find this unique solution. So I hope that after working with these neural networks in your exercise, you can appreciate this problem of having these very many local minima and why it's nice to have a unique solution. So good predictive power, and it's not an, well, having a unique solution, that's more of a theoretical result. On the other hand, in terms of disadvantages, if you take, for instance, the RBF kernel, then the results will really depend on the way you scale your data. So it's not invariant to data transformation in general, and not even to scaling. I mentioned this explicitly because other methods do not have this limitation. Particularly decision trees are robust with respect to that. Training can be relatively expensive. So if you're lucky, you get a sparse solution out, and then testing can still be fast. But training compared to other methods is an expensive process. Another property is that, as I've presented it, it is not a probabilistic method. So in particular, these predictions given by sum over I, alpha I, yi, xi transposed, and then your variable x, they cannot be interpreted as probabilities. They're not between 0 and 1. There is a probabilistic of formulation of support vector machines, the relevance vector machine. But SVMs themselves are not, do not enjoy probabilistic interpretation. Another major limitation is that out of the box, it's applicable to binary problems only. So if we want to do digit classification, then I have to train, for instance, 0 versus all, 1 versus all, 2 versus all, and so on. And other approaches have been proposed, but the basic SVM only works for binary problems. And then, well, you have this choice between kernels, and you can also construct kernels for particular applications, which you can see as an advantage or a disadvantage. So it's your chance to inject prior knowledge into the procedure, but it also means this is a design parameter. And when I say training is expensive, I mean both the cost of the quadratic program, but also the optimization of the design parameters. So there have been papers with suggestions on how to estimate the parameters, but essentially what most people do is grid search and then via cross-validation to find out what works best. So for instance, a grid search, if you use the RBF kernel, you would do a grid search in which you modify on the one hand the width of your kernel, and on the other hand the penalty on your slack variables. So, pretty brute force. On the other hand, something that carries over to other problems is the kernel trick. And this has been a bit of a revelation to the community. And subsequently, many other methods have been reformulated in terms of the kernel trick. So PCA, for instance, exists as a kernel PCA. You can do kernel regression. You can do basically kernel everything. So most classical algorithms can be rewritten such that you don't have single observations appearing, but inner products of two observations, or between an observation and your query point. And if you can obtain such a formulation, you can automatically and immediately use the kernel trick. So that is good. Okay, do you have questions? If not, think about them. I'll ask again after the break. So this was the basic SVM, which takes just feature vectors as observations and looks at labels that are just class memberships. And after the break, we will look at structured output or structured SVMs, methods in which you can predict, well, objects with more interesting structures than just a class label.